Today we have our new postdoc, Wendler, who's going to talk about a new approach for trying to understand this great mystery of diffusion models and know so much. And we know so little about what they're doing. So, I'm really looking forward to hearing what he's found.
All right, I'm looking forward to explain a bit. So I will start like a bit jamming on your anecdote that like research is kind of also teaching. This project initially started as a class project in EPFL's multimodal course. I don't know the exact name. So Slava and a colleague of him, Vyacheslav, shortcut Slava, they implemented SAEs on SDXL Turbo, and they had something that looked kind of cool. But like when he came to me, his interventions kind of didn't influence the generation at all. So they started out with the classical settings that you find in the Anthropic blog posts, like expansion factor 64. Yeah. And he was like, can I do an internship with you? So I asked around, and I was really lucky. I found Shalar, who had some money for this project. So we were able to hire this really amazing student, like he's a force of nature, and gave him the, platform to execute this project. So we have a big team. Yeah, we have Mikhail. Mikhail, he always joined my reading groups and is really interested in interpretability and in AI safety. He was really interested in this interpretability project as well. Justin is our diffusion expert. He literally wrote up the entire diffusion math for me because I thought I needed it in the paper. We ended up throwing it out completely, sadly, but we have it somewhere. Amazing. Bob, really amazing prof, and Shalar, who made all of this possible. Yeah, so let's get into it. This is something that you can do. So here we turned on like an animal feature on the face of this model. And you kind of can get like some hybrid in between human and animal. And you can also get, as you change the feature strength, it will interpretably affect the image. So I think like most of you know what Sparse Autoencoders are, but like we are gonna do like a very brief recap. So it was considered an interpretability breakthrough. I guess people were really excited. Now finally people are like getting more sober about it and are like, wait a minute. But like with this method, you can, in an unsupervised way, find like seemingly very interpretable directions in your intermediate results of your neural network forward pass. And like for language models, they have been scaled up to the largest language models, and Anthropic trained some of them on Claude, and they found like this famous Golden Gate Bridge feature. So the plot is quite overloaded, but like focus on just the activation level on the bottom. You can see like if you have a high activation level, if you look at the examples, they are about the Golden Gate Bridge, very specifically about the Golden Gate Bridge, independent of the modality, and also at lower positive activation levels. This is like a bridgey like feature. It gets excited by bridges. But why bother? Why do we need even to learn these interpretable features? Like, couldn't we just look at neurons? So we have like this kind of ancient insight, basically since the beginning of deep learning, because this is when people started optimizing over the image domain in order to excite neurons. That neurons are kind of polysemantic a lot of times. So the same neuron can respond to different things. It can respond to dogs, but it can also respond to mazes in this synthetic example here. And like recently, people came up with this superposition theory. Like it's more like a hypothesis. It's not really a theory that makes predictions like theories that you have in physics. They came up with this explanation that could be underlying this polysemanticity phenomenon. And it basically addresses the following puzzle. If you have only 2 neurons, how can you represent 5 features? Right? So 2 is kind of smaller than 5, so you probably are not going to represent like a feature with a neuron. But if you put vectors onto the 2D plane, you can kind of put an arbitrary number of vectors there. And as long as the features don't co-occur all of the time, this is where the sparsity comes in. You are able to like nicely represent your 5 features most of the time. And that's called superposition, basically putting the features into the space in a non-orthogonal way. And the idea of the sparse autoencoder is now, hey, given that, usually in the internet you have more than 5 concepts, more concepts than neurons, maybe like language models and stuff do something like this. So maybe we can try to learn to invert like this process and convert like the activation vectors into some representations where the features are monosemantic. And this is the SAE. So you take in your activation into an encoder, you blow it up into some larger representation. So in this synthetic example, we know the optimal value, it is 5. Usually you don't know that, which is a big problem. And then you just optimize your encoder-decoder pair, to faithfully represent the activations under this sparsity penalty. And the idea is like from observing a bunch of activations, you can now get like these true features in this idealized setting. And maybe these features are the right abstraction in order to get monosemantic interpretable features that also causally affect the forward pass. And like for language models, this has been very strong and useful, I guess. So the student, Slava, was asking whether he can do this for diffusion models as well, because they are much cooler. And like just a brief reminder, diffusion is this thing where you add noise, and then you train a neural network to remove the noise. And recently, we also have like few-step diffusion models that can do this in between 1 to 4 steps. So how does a diffusion model work? You give in like some noise and a text prompt. In SDXL Turbo, you have a UNet architecture, like I made a very simple image here, and out comes like an image corresponding to the caption. And I mean, this would be the one-step generation process that we focused on. So we are kind of cheating a little bit. So we removed like this multiple time steps layer of complexity that you have in actual diffusion. So maybe you can think of it as a GAN. Okay, but our SAEs also work in the multi-step setting, as I will show in the demo. So we train SAEs on the updates performed by these blocks. So here I have like a more detailed diagram, like this is actually how the UNet works. And each of these blue blocks is actually a whole transformer, like a transformer with self-attention layers, where the batches of noise, or the representations of batches of noise are allowed to attend to each other, and cross-attention layers, where they are allowed to attend to the text prompt. And you also have MLPs in there. And yeah, so we focus on these blocks that contain like this a lot of transformer layers. And
sorry, so could you go back? So
yeah.
Each of those down projections are, you said those are each transformer layers?
Well,
each of these
this is
blocks,
it's actually a transformer.
or is this just a traditional UNet? Right
I mean, the whole diagram is a UNet.
Right.
But like if you zoom into one of these blocks, like let's say down
I see. Okay.
1, 0, that's a transformer.
Okay.
Consisting of multiple layers, containing multiple self-attention layers, and also sometimes multiple cross-attention layers. And
Okay. Yep. Gotcha.
okay, so where to train the SAEs, right? We are in academia. We kind of don't have infinite compute, so maybe we can be smart about it. So the first thing that we tried was just go in and turn off a bunch of layers, right? And see how this affects the generation. And you can see like not all blocks are created equal. The ones in the middle kind of have like a big impact. So, and because we are trying to fix like this causality aspect, because the student already has SAEs, we will zoom in on those. And
sorry, and he uses concatenation, right? For the down blocks going to the up blocks that are the same size. This type of unit, because some units do different things. So is it you concatenate?
You skip. You have like a residual connection from the input.
Right, but is the residual connection, is that concatenation?
No, that's addition.
That's that's addition. Okay.
Yeah. Okay, so we identified these blocks. We also ran some other prompts. So here we just turn off the update performed by this block. So that's the forward pass where, like, yeah, you just don't update the residual stream with the update performed by this one transformer block. And yeah, it was really funny because so we did this, and afterwards I was going to my colleague Peter, who does the data engineering or did the data engineering at Stability and now is at Leonardo, and he was like, "Oh yeah, I know this. You know, like there is this YouTube video where this guy calls this the composition layer, and this other layer he calls the style layer. So there was a guy training like low rank updates on these different layers, and he has like multiple multi-hour YouTube videos. He's completely like a machine and amazing. And yeah, I wish to know the things that he knows. But anyways, so that's this video. And
wait, so quick question. So in your figure, you have block dot attention something. Go previous slide.
With the images, yeah.
yeah.
So these are like I forgot. Are you still training SAEs or if this
Okay,
is
so
this is just zero ablation or something like that?
No, here we just set these blocks to 0.
Zero ablation.
Yeah. So the naming in the figure is a simplified naming. So these are the actual block names. In this figure with the images, these are the actual block names. In the diagram figure, these are shortcuts.
So this is what happens if the output of these blocks were not summed in.
Yeah. So
okay.
Yeah. So you would basically bypass it by going along this.
Okay.
By this line.
Okay.
Okay.
Yeah.
Hey, Chris, I have a question.
Yeah.
So this was mentioned a couple of times. You said composition in these models. So can you explain what that composition means?
It composes the elements of the scene. So this guy can literally create a cat. Or so I will show this in the interventions. So
Gotcha.
this is just, it is like not clean cut and very hand wavy calling this composition.
Mm-hmm.
So it's by no means an accurate characterization, but like if you turn on in this layer like a cat and a dog feature, you will end up with a cat and a dog in your image. And if you do this at other layers, you will maybe locally, you know, turn on some hairiness feature, or something like that. But we will get to that, I think, later.
Awesome, thank you.
So this is where we train. And yeah, just some more details that actually are not really written on the slide. This F thing here, like if you do like a single example, a single noise, right? Then in this, so we are kind of in the smallest spatial resolution of the unit here. So if I remember correctly, these were like 16 by 16 by 1280 tensors. And we train, like we feed in the 1280 vectors into our SAE. So we don't do anything that would like make similar spatial locations.
So sorry, you vectorize the 16 by 16
Yeah, but
and then you,
yeah, I'm saying we have weight sharing across the spatial locations.
So he doesn't vectorize it.
okay, I see, yeah.
So we don't say, look, you should. We don't bake in this prior assumption that maybe would be reasonable of like neighboring things should be similar. But this is the first work, so I think it's a fair thing to do. This just makes everything super easy on the engineering side. So we do a bunch of forward passes. We spam our hard drive on the cluster with like 50 terabyte of tensors. And now we can iterate over some SAE parameters to get some config that actually does something. And this was the first intervention that worked. I think this was maybe at ICLR last year or ICMR, I don't remember. Slava sent me this picture. There he turned on the ball feature in the compositional layer, and it actually causally affected the generation. So this was really cool. And before that, like when we had like a larger expansion factor, we would need to turn on like 17 or something ball features, and then we would create a gray blob. Like, and now, you know, now we have this, which is really cool. And
Wait. Yeah, sorry, you can go.
So if you like triggered that ball feature and the face looks like a ball, how would it differ when I would have a direct prompt where I would say, like add a ball feature along with the face, or I will compose to diffusion inference where in one I will have something with the ball and another I will have something with the face. How the generation differ?
yeah. So you're asking like, how close can I get to this result by using prompting?
Right.
I don't know. I think that would be an amazing experiment to run, and maybe we can add this to our paper or to our to-do list. Yeah, that's a question that I keep having all of the time when people do these things. Yeah, but like I think we will have some features that, to me, I would be really surprised if you could do that with prompting. But maybe you could do it with layer-specific prompting. You know, where you have different prompts for the different blocks. Yeah, let me just note that down.
You know, the strength of this approach is also that you can continuously vary the strength of this intervention.
Right.
I wouldn't know how to like get prompts for each individual image.
Right, but they have some hacks that you can write like a word and then colon a number, and then this is kind of
Oh wow.
You multiply the embedding or something of this word, and you kind of can emulate this. So that, I mean, so another thing why the image domain is really amazing. David knows the most about this. Like people have done everything. People have done everything. You cannot imagine what people have done on GANs. Like the stuff that we are doing with language models is baby stuff. People have done everything. Like, anyways, so you impossible to come up with anything new. Honestly.
Wait, could you go to the previous slide? Just quick clarification question.
Yes.
So here you train 3 different SAEs for 3 different layers, right?
4.
4? Oh, sorry, yeah, 4.
Yeah.
Okay.
But so, spoiler, only 3 of these layers I would say have, I mean, they all specialize, but only 3 are really like interpretable if you hold them to this standard that features should react, or they should be on similar looking dataset examples, and then they also should causally influence the generation in a way that matches.
Okay.
So then only 3 of these blocks are easy to interpret, but the middle block, like Slava managed to pull out some features that are really cool and like, but they are so hard to interpret. Like they do something like when you look at them, some of them, they do something really that makes sense, that does something with the perspective and with surfaces in the scene, but they are kind of hard to find, and it's super hard also to label. But like, so they do something. Just okay, we get 3 really interpretable types of SAE features, and like this one mysterious one. Yeah.
Which one is the mysterious one? The up
It's this one.
mid one.
Yeah.
Okay.
The mid one is a mystery to me.
Okay. Sorry, one more question. So the ball feature that you actually steer,
That is here.
that is here, and that's only there. It's just like one dimension,
That's one vector.
just one vector. Yeah.
Yeah, we just like we learn, like we have like maybe in this example we had an expansion vector of 2. So we go from 1180 to 2000 something.
Okay.
And then we select like one vector.
Yeah.
So that was active during a forward pass with a dog playing with a ball. Like we look at what is active in the ball, and then we grab this guy and add it.
Okay. Makes sense.
Yeah.
So yeah, I also have some questions on the same slide. So you train SAEs on the outputs of those modules?
Yeah, on this F thing.
Okay.
Yeah.
And
so it's kind of a bit confusing where the red arrow is pointing, but yeah, so it would be here, like the stuff that comes out of the down block.
okay, so not on the residual stream, like
No, not on the
output of
residual stream. Yeah.
Okay. And another thing
So
is
something that we should maybe also try, but like everybody's doing something else now.
yeah.
Kind of.
Mhm.
Yeah.
And another thing is that what are the shape of these lower resolution images?
That is 16 by 16
this is-
by 1280.
This is still a 2-dimensional image, right?
Yeah. I mean,
like
it's
2-dimensional
with
data.
a ton of channels. Yeah.
With a ton of what?
Channels.
Channels. Okay. And you blow it up by how many?
Just a factor of 2.
Just a factor of 2.
Yeah.
And that gives you interpretable results?
Well,
Like just a factor of 2, that
smaller,
means 4, right?
the smaller your expansion factor, the stronger your interventions.
Yeah.
Okay.
In our experience. I mean, we don't really care about capturing all of the features.
The smaller your
Like,
expansion factor, the stronger the intervention. That kind of like makes me think you should be able to get the strongest intervention by directly messing with the channels, right?
But
And
by what?
by directly messing with the channels, not even training with that.
Oh
data.
yeah. I mean, no, because you can have 0.5. you can have
yeah. You can have 0.5 or anything like that.
Yeah. Yeah.
Did you ever try that?
Oh yeah. Slava did 0.5, and then I was like, this is weird. Like, we shouldn't put this into the paper. People would just be confused. But the 0.5 ones are.
Works even better.
I mean, they are causally strong. Yeah. I mean, I maybe they are not as monosemantic because you have again this combinatorial argument, right?
Well, I mean, but empirically, it's a
Yeah.
question. I think the argument is one thing, but I think the experience the question is.
Empirically, they are great.
Uh-huh.
Yeah.
They're great, and you can achieve the
Empirically,
causality.
like one other thing that we did before training the SAE is like to just get a feeling of which blocks do what was also activation patching. And that also, like in the middle, we patched like a dog head, like the activations that were in a dog head, we patched it into a cat forward pass. And at the down block, we can get a cat dog. Like a chimera, how do you say this? A chimera animal. And I mean, obviously, as you go up the layers, the more this looks like literally going into paint and cropping a part of the image and like, copy pasting it there. Yeah, so this was really fun.
How robust is this ball behavior to the prompts? Like, does it work?
So that's a great question. So the down 2-1 thing, the composition, the thing that we call composition layer, the thing that actually creates elements in the scene, that one is super duper, that one doesn't care about what is the prompt. But for example, the up00 block, that one we found is like really, it needs the relevant context to do something. But if the relevant context is there, it is also strong. Like, so that's, we call it a detail layer. And also like same for the up01, that one is a style, we call it style layer. That one also is better. I mean, that one will also generalize wildly across prompts, but like that one will really locally change like the texture and stuff of whatever is the object there. So, but I will show you hopefully some of this in the demo.
Chris, I have a question.
Yeah.
What's the input shape for your SAE?
That is a vector of length 1280.
So that means you are assuming that you're not assuming any spatial
Yeah, so we do this simplification. Yeah.
So do you think that if you had so if you're doing linear SAEs, would that still capture, like it seems like it's capturing some spatial information, like you could transform a person into a ball?
Yeah, so I mean, like one thing that is really weird and that I learned about this unit is in this architecture, they actually don't use positional encodings or anything, but by virtue of how the convolutional layers and so on work, the model can still learn positional encodings. So you can probe out like the spatial locations from these 1280 vector. You can literally probe out, I am at position ij. So all of these layers are position aware.
Right. And I think that's like really interesting, where you didn't use any spatial processors like convolutions.
Yeah.
Just by looking at the channels, you were able to get spatial features. I think that's very interesting.
Oh yeah. So I think we will see more of that, I hope. Yeah. David?
Oh, when you do the intervention.
Yeah.
Or maybe you're going to talk about how you do the intervention in future slides. I was just going to ask.
I think maybe in the demo it will be very obvious.
Yeah. Are you doing the intervention on all 16 patches, or are you doing?
No, so we built a UI. So we do everything, but like the best thing that we can do.
The intervention.
Yeah.
Okay.
We have a UI. You can paint a mask, and then we just collect the indices that fall inside of this.
Great.
The mask. But so one thing that's worth noting, right? So you like in this idealized way of thinking, where you are like, oh, the SAE literally is supposed to discover the true features. You could just set the SAE coefficients, right, to do the intervention, and replace the output with what comes out. We don't do that because our SAEs actually have a kind of large approximation error compared to also what you see in language models.
So you just add the vectors?
Yeah, we add the vectors. So we circumvent this issue of having actually a bad reconstruction. Just an important detail for working with SAEs. And like I think SAE interventions is something that is not well understood also in language models. Like, especially in language models, I would say. Okay, so let's go and look at the layers, right? We did different types of visualizations. So here, to start, we just generate an image for this prompt. a cinematic shot of a professor sloth wearing a tuxedo at a barbecue party or something. And the rows of this plot are like the 5 SAE feature indices corresponding to the SAE features, you know, that reduce the L2 error the most. And we plot like a heat map showing their coefficients. So red means this feature is very active somewhere, and blue means it is like a little bit active, and transparent means it is not active. And then we have like visualizations where we subtract the vector corresponding to this feature index with a multiplier that you can see in the column name. And that kind of influences the generation in like sort of like ablating. Like semantically, this looks like ablating the feature. And here you already notice some ugliness, I think, of what we are doing. Because like if the theory would be nice, ablating should be just setting this value to 0. But instead, to get like an ablation-like effect, we need to subtract it with a factor greater than 1, right? And but then you see that, for example, the first row, the light chains disappear. The second row, also the light chains disappear, and also some of these tent shapes. The third row, you lose like your sloth animated face. And the last 2 rows, they do something with the tuxedo, I guess, but they are less nice. Then you can do the same thing, but just increasing the strength. And first row, I guess the light chains pop out a bit more. Second row, you see there is like tents on top of the tents. And last 3 rows are more subtle. Then what we also can do on this block is we can turn the feature on the empty prompt. Like, so here we do a forward pass with the empty prompt, and we just turn at the down layer, we turn everything else off, and this guy on. And so it also pulls out like the kind of matching concepts usually. And then we also have the dataset examples that also match.
I have a question.
Yeah.
You chose the features that minimize the loss or affect the loss the most.
Right. So because we are generating a prompt, right? Yeah.
Are these also the features that happen to activate highest?
Oh yeah, that's equivalent, right? In this, that's equivalent. I mean, wait. I mean, it's
if my down projection is
to
like a
right.
kernel,
yeah
0 dimension, whatever.
Right. Okay. I think I explained it wrong. So if the down projection was orthogonal, it would be the same.
Yeah.
But it's not. So maybe it is just the features with the highest activations. Yeah. The ones with the highest SAE coefficients.
Nice.
And I mean, it will also be relevant to the loss.
Absolutely.
But yeah, not in this way that I was talking about it.
Okay.
Maybe we should put them side by side and check.
Another quick question. So generally, what does the diffusion model generates on an empty prompt? Is it consistent?
Yeah, that's a great question. So Turbo is actually kind of collapsed, as Rohit shows in his recent amazing work. That would be so cool if we could combine it with this. So we have better images. The empty prompt is usually like, it looks like a drawing of a landscape with a lot of brown. You have a little bit of grass. Sometimes you have a tree. Sometimes you have like a person-like thing in the middle. So it's definitely polluted by the features that are. So these visualizations are you see how the features that we turn on mix with these brown tones and this painting style. Like for example here, where you get like this drawings of this, I don't know, hamsters or whatever this is. Okay, so this is the block that we call composition block, and we call it that because you kind of can connect a lot of the features with elements of the prompt, right? But by no means is this an accurate characterization of the block. But it helps to think about it. Are we good? Are we good with this block?
Mm-hmm.
Then I will.
On the data set examples,
Yeah.
is this just from, you have a data set of many prompts and then you just generate a lot of things?
Yeah.
Is that?
Yeah, so actually, I wish the dataset examples could be even better, but so we were kind of pragmatic in keeping things cheap. So we pre-computed a few hundred of million of prompts, latents for prompts.
Mhm.
So that was the 50 terabyte of latents on our disk.
Mhm.
But like to get these dataset examples, we actually only looked at the first 50,000 or something in that ballpark. So maybe we don't cover the whole data
Cool.
nicely.
And what was your source of prompts that you used to?
That was Koyo and Lion, I think.
Cool. So like training data sets.
Yeah,
Nice.
yeah.
Mhm.
And that is this block. I had like a back and forth with this block. At the beginning, I found it kind of boring. At the end, it was my favorite block. So I ordered them here not by their order in the forward pass, but their how interpretable they are order. So this is the style layer. And I mean, there are so many things that are kind of cool to me in this layer. For example, you often have like this 27 feature that kind of increases the illumination effect when you turn like crank it up, and when you subtract it, it has like it makes things looking darker. And so the style layer is also still strong enough to do something on the empty prompt, right? So it will create this texture like images if you turn it on the empty prompt. And also similarly on the first row, you have something that seems to be shadow-like, at least when it's on.
What's the opposite? Interesting.
Yeah, and they activate on different parts of the image, right? So this one is more on the left side here, and this one is more on the right side here. And then you have all sorts of other things. Like you also have like this light bulb texture, for example. And you have like this one, the last row, I think that should have a name, but I don't know what's the name for this, but
It's like red versus blue.
Color temperature.
yeah. Color temperature, I think, yeah. That was the name that I was looking for.
Yeah, it's warm, cool. Daylight, indoor light.
Okay. So also like one comment, recently we had like this related work coming out that showed that SAEs also learn interpretable features on randomly initialized models, like without training, which is why I think the causality aspect that we have here is really important. So I highly doubt that your randomly initialized UNet can create images matching the, interpretation of the feature. So this is to me the key to making sure we don't do something trivial. You know, because like random, like people for many years used like random Fourier features and stuff to build their classifiers. So there's like, yeah, there's just this risk of fooling yourself. Okay, style block. And the last one that kind of is interpretable is like the detail block. Detail block doesn't do anything on the empty prompt, which is why these columns disappeared. And we have more dataset examples. But detail block still, if you do something in the relevant context, like the context of the prompt, you can get strong effects. Like detail block can also add some party decoration, or also remove it. Detail block can nuke your mouth away in this fourth row. You just nuke the whole into it. But I mean, these interventions are hilariously strong, so we are really butchering around here.
Do I
Yeah.
understand correctly that you did this analysis on 4 blocks based on this YouTube video, or did you?
No, we found our blocks ourselves, but just people knew already that 2 of these blocks.
But my question is,
yeah.
did you select these 4 blocks, or did you do it on the entire unit?
Yeah. So we were kind of GPU poor. Well, not really GPU poor, but like constrained. And we were like, we want to do as little training as possible and have as great interventions as possible. So we did these preliminary experiments to narrow down the blocks. But like, but maybe someone should do it.
And the preliminary experiments are the zero ablation.
Zero ablation and activation patching. Basically intuition building about the forward pass.
Chris, I have a question.
Yeah.
For your interventions, so do you just use the heat map to select the pixels that you're gonna intervene on?
Yeah.
Okay. It seemed like the rest of the images.
Yeah. That's a good sharp observation. I didn't mention this. Yeah, we use the heat map to turn it on and off locally. Except for like this thing where we turn things on the empty prompt. There we just turn it on everywhere. Okay. Also the dataset examples match kind of the interpretation or the stuff that it is doing in the forward pass. And then we have like also this problem child block, where the interventions basically don't seem to do much, but like the dataset examples are very, very neat. The dataset examples look like you should be able to do something with this block. But yeah, we didn't manage to pull off like so this is the block where literally like Slava, he spent like I think a ton of time, and he can pull out like a list of let's say 10 to 20 really interpretable like features that have a causal effect on the generation.
Would it be that you're just not using the prompts that have effect?
Yeah, but like, so I mean, these are the 5 most active features in the Tuxedo Professor Sloth prompt, and now we are just locally cranking up and down the strength, and yeah, it warps the. It has some subtle effects that are really difficult to describe. Whereas, like, if I look at the dataset examples, like in the 4th row, I would say, this is the left boundary of an object. Or in the 1st row, I would say, this is the right side of a head. You know? And on the 2nd row, I would say, this is the left side of a head. And then we also have some features that I would characterize as like, this is the leftmost object, this is the rightmost object, and so on, like by looking at the dataset examples. But yeah.
So, so one of the things that we're finding in these transformers, right, Nikhil is like, doing whole papers on this, is that a lot of the important features are not values,
They're pointers.
they're pointers.
Yes, pointers.
And so is this a pointer layer that's laying down
Maybe.
pointers for the geometry of the scene that you've got? And so, it has no effect to, like, maybe the intervention to try is you could, instead of amplifying things, you could try moving the pointers around to see if you can
Right,
rearrange the
right.
scene or something like that.
Yeah, we should do different interventions.
Right.
Yeah. Good idea.
That's what you would do, right, Nikhil?
Yeah.
Yeah.
Move them around.
Switch left and right.
It's actually not too hard.
Switch the dog and the cat.
Yeah.
That kind of thing.
Yeah. I like it.
Mhm.
Yeah, we should try it. Okay. So that's the layers. I'm sorry if this slides are, I don't even know how much you see here. So I see it on my screen. So I don't know how horrible this part was.
No, looks good.
Yeah.
So one suggestion for presentation, just as a note,
Yeah.
is that in the dissection work, we found that when we showed heat maps, it's really hard for people to read and understand in paper. So we just binarized the heat maps and show these little window things. So you can see, and there's a few of us who are using these little window visualizations in these kind of vision papers, where you just show where the highest activation. It's just easier to read.
You mean you just remove the non-active part?
So you gray it out to like 70% gray so that people can still see it if they want to. But then at 0% gray, there's this transparent window. You can even draw a border around the window or something like this. Say this is the area.
Actually, we have that.
Yeah. It's a little bit clearer
We
visualization.
do have that.
Yeah, it's good.
Okay, so this was some early. So now we are turning features on a different context, and these are some of the early features that I found that are. So these are heavily cherry picked, just as a warning. That like have a really cool and interpretable effect like across different prompts. So we sample a bunch of different random prompts from our data set, and I turn on these few features that I found. So the first one, I guess, is some comic feature. The second one, I tried to find the anime feature, but in the past I had some better anime features than this one, but this was the one that I found when I made the presentation. And the last feature I found when I generated pictures of an angry monkey. So that's somehow an evil character feature. So it grows, the horns. So really cool stuff, honestly. Oh, never mind. I'm sorry. Like the left side was actually the dataset examples that have the feature, and now the right side is turning them on unrelated prompts. I'm sorry. So the first row is always the picture of a colorful model that I use the most to play around, and then we loved the dog that plays with the ball, and the classroom I found just funny with the angry feature down there.
I have a question.
Yeah.
Have you played with the order of the prompt? Like you change.
No, I didn't.
Okay.
But
I was wondering if
you are referring to the text encoder being weak?
maybe, or like
Yeah.
if it has any effect. On
Yeah.
it.
So actually, we are playing right now with the text encoders a bit in flux, and we found some cool stuff. But that's a good idea.
Maybe the features are there and they might have very good activations, but just due to the order of the prompt, maybe one of the features is far from the end where the decoding takes place, and that's why you don't. Although like the feature is there, but it's not getting activated because of the activation and the order,
So
like
no,
and the position of those adjectives.
but like we are decomposing the update to the noise, right? So whatever was in the prompt, if the units, if the cross-attention blocks wanted to attend to that, it's in our grid, right? So that is the difference of our work to the other works that do SAEs. Is we are literally doing it inside of the unit and on the visual features. So other people did it on text encoder, intermediate results. They did it on clip embedding vectors that you can use to condition some diffusion models. Those are, and the results are really amazing, and were what motivated us to believe, like, that actually gave us the conviction that we also can get interventions that are like affecting the generation. Those are done by Giddis, who is a nice guy. He also was in meetings with us. Yeah. So I have some more of these, and then I would like to do an interactive thing.
So did you attempt to sort of quantify interpretability?
I mean, yeah, of course.
And what kind of your method did you use to quantify it?
Yeah, so like the quantitative analysis, honestly, I found it very challenging. But like, so we had like this we were lucky we had like this down layer that actually modifies the images in such a strong way that like even kind of dumb models like GPT 3.5 can label the features. So we auto-annotated the down block, and we did the usual, we computed some of the usual scores of like how specific is this feature, how sensitive is this feature, and how causal is this feature. You can find this in the paper. And we tried to make the point like more quantitatively that these layers are specialized to different things.
A related question.
But this was really hard and it's not super convincing.
So did you like have a baseline that you compare to that you beat, like a PCA decomposition of the feature space or something?
We did a terrible job on that. We do have some baselines, we do, but they are kind of weaker than PCA.
I see.
Maybe just a neuron baseline.
Yeah. Yeah. I mean, like the baselines, I think that's really important.
Yeah, if you're still going through peer review, like this kind of thing.
Yeah. It's just like we are resource bottlenecked.
Sure.
Currently, baselines, PCA. I mean, we have this. We obviously have this in our to-do list.
Yeah.
Or
the neuron baselines.
Yeah.
Another thing I wanted to ask. This is also related to baselines, but baselines for the causality effect.
We actually started looking at the neurons.
Cool.
We just didn't go all the way. They were not great.
Yeah, which is good.
Yeah.
You can beat them.
Yeah.
So this is kind of like baselines for the causality effect. So you have found that these specific neurons which turns on the anime neuron and the anime feature in the generation, right?
Yeah, or the horsiness.
Yeah.
Here in the first row.
So let's say you try to learn some sort of like a sparse but linear combinations of the feature of your SAE basis directions that you have found, and just to that reflect that basically turns on that anime feature, like without selecting it. Okay, this is the anime direction, I'm gonna turn it on. How about you just learn it?
Yeah. So there is like this related work that does this for language models, right?
Yeah, there are lots of related works.
Language
models,
right. Yeah. So sure. Yeah.
So
but also like just not doing SAEs.
So what?
Just not doing SAEs and learning them directly. Like Rohit did with the sliders.
Yeah, so
it works even better.
So then my question would be,
like,
let's say if something turns on the anime features, is it actually the anime neuron or?
Oh, that's a great question. Yeah. So, well, I mean, I think like what we see here is that certain blocks lend themselves at least to more effectively learning certain. Like if you want something to affect the style, you probably have an easier life to do that in this up01 block, right? But like that is something that we should try. Yeah, I mean, I noticed with low rank updates, you're actually quite flexible. Which exact parts of the attention I mean, some of these are even equivalent mathematically. Which of these parts you update, but like usually there, people update all the layers. So if you, I think that's an interesting direction to localize the LoRa updates onto layers, and yeah, I mean, if the layers are specialized, this will kind of upper bound or what you can do. So yeah, it's really a hard question. This like whether you found like the real thing. Yeah, I don't have like super deep thoughts about that.
It's okay. Thanks.
Yeah.
I was just wondering about your GPT 3.5 interpretability pipeline. Is it
Yeah.
like you give it 2 images and then ask?
Oh no, like we do we follow for closely the footsteps, I guess, of the anthropic work where you bin your images into different activation levels, and then you are like, look, here are like, I don't know, 5 or something, whatever we can afford.
For each feature.
Whatever prompt length we can afford. Here are 5 examples where it's not on. Here are examples where it is 10% on, 25%.
Nice.
And please.
Explain it to me.
yeah. And so the down block is the block where this kind of makes sense. But already the up01, that is very interpretable. Like the models focus on the foreground object too much, right? And you don't want to introduce too much of like hand holding, I think. Yeah. You don't want the auto annotation pipeline to be prompted with like focus on the style and then afterwards make the claim this is a style layer, right? Yeah. So yeah, we have that in the paper. Slava has the features annotations somewhere, but I think you don't even need them. You can just generate a prompt, generate an image for a prompt, see which features were active there, right? And play around with them in another prompt, which is what our app allows you to do.
I was wondering also, you have like all these different layers.
Yeah.
How do they communicate? And
oh, that's we didn't get into that yet. That would be a really exciting direction, I think. Yeah. So we cited like Sam Mark's work like at 3 different locations in our paper, like so saying like, oh yeah, more advanced methods would be cool. You know, that kind of try to connect the features, and future work, you know, should do that.
nice.
And yeah, maybe you would find even wilder stuff there. So this is the same plots for the style layer, just turned on everywhere, which is not how you should use the style layer, as I'm going to show you in a bit. And even more. So the funniest is like turning off the lion main on a lion. Like when you then.
Oh, which one?
Here you have like the main, and then it just has like big cheeks.
Are those ears? It's hard to see. Oh yeah, you can see like the lion's ears sticking out or something.
Yeah. So we're gonna see something in a higher resolution now. So assuming that we still have some time. So depending on how slow this is,
Sure.
we also have like a Hugging Face demo. It's just slower. So, and I mean, like here is really some of the amazing things that also happened. Like let's say, like we want a higher quality image, so we should use 4 steps. And let's use my favorite prompt, which is a photo of a colorful model. Okay, let's start from that. Okay, so this is the image. Let's find some interesting feature like this is one that I just think makes an amazing effect. So now we generate a photo of a giraffe. Here we see the features that are active. On the down block, this is the composition block. But like, I want to pick out the giraffe style. Like it's 3, 7, 1, 8. 10 is kind of strong, so let's use 6. So now I can locally turn on this giraffe texture. Oh, I'm in the wrong layer, so this won't do anything interesting. So this one. And you get this amazing,
whoa!
You get this local amazing effect.
Wait, but I see you blacked out like the cheek and the forehead, but then on the left side of the cheek, for instance, it still
It
changes.
got it anyway.
Yeah.
So,
but
The
like
amazingness of Transformers attention.
the neck doesn't get it right.
Even change the hair.
But you have bilateral
Yeah.
symmetry.
It
And so
is
something is like enforcing this.
yeah.
more than, but like I think this is as specific as the edits get. So this is already the like mutating not super much. For example, like another cool thing that you can do is like very, I don't know.
That's a beautiful example. I love it. And that's the style there. That's one you call the style there.
Yeah. Let's do a bit more. Just because I love this stuff. Let's do like let's get some hairy textures, like 4, 1, 4, 7. And let's see what happens.
You have to paint a different area.
I mean, I can.
Paint the hair.
So it made some
It's so cool.
hairiness. And we can do this. We can do this on different layers, of course. Right? So let me just remove this. So I found some fun stuff. Let's go to the composition block, right? So I guess so. I start with the everything is nice kind of example, and then let's go to something where things are not as nice. So 199 seems to be something with a head. Okay. 199.
In the up layer.
We go to down, and the head should be, I guess, on top. So let's apply the head intervention.
Oh, you can get a hat.
We can get a head in the composition layer. So this is like, this is how I would sell this to investors. But we are scientists, right? So let's take the beard feature or whatever.
Money anyway. We don't have much.
So I also show you the ugly. Okay. So 4, 5, 2. Okay, let's draw a beard. Beard, I guess. So this feels like I typed the wrong number.
Oh.
No. Okay, then let's make it a bit stronger. No, this is like, this is unheard of. This is really ugly. This is like the demo failing. Oh yeah, we need a really high number this time. I don't know why.
It's doing something with her cheeks.
Yeah. No, okay.
Oh, wow.
So, well, but it is, so we were fooled. It's not a beard, it's a manliness or something.
Right.
Right?
Yeah.
It was not a beard.
Interesting.
So you need to be careful with your interpretations. Right? But like now let's do something really, really cool. And so now like this is the stuff you only see when you do this research. And so now we take like the detail layer, and it also has something that does something with the beard, right? 3742. And now we get like really the weirdness. So this is the layer that we found. This is context dependent, but it also can be very strong. And it kind of makes sense, but it makes something that you would never get otherwise. Right?
Oh, what is this? How is this one different from the previous?
Previous, I think it
Different
turned
layer.
or returned to a man.
This is, wait, so this is.
This
a
is
different
like
layer?
much more local.
Oh,
Yeah,
wait, so
different
this is a different
layer.
layer.
Yeah.
Very
Like
nice.
This one like gave her a beard, but she's still a woman facial structure.
But last time it didn't even like it. I mean, it creates some hairiness, whatever. But
Perfect.
like,
Perfect.
so this example is actually better than what I got last time. Let me just download this.
We'll put this one in the paper.
Burn some of the colorful paint into hair.
Yeah, like let's try different strengths. I think you know sometimes I write photo with F, sometimes with PH. So now it's not strong enough, I guess.
Interesting.
So it's interesting. It's like a step change with strength here.
Yeah.
Like at a particular strength, she just has a full beard suddenly.
Yeah. So everything that I show you guys is heavily cherry picked. Oh, now I have what I had last time. So yeah, this is it.
Well, thank you very much, Chris. What a great presentation.